by that is integral of x minus a to the power n dx equals x minus a to the power n plus 1 over n plus 1. So whenever you see this, means that it's always 0 if x is less than a. It's the truncation. So this indicates truncation for x is less than a. Okay, this is true if n is greater than or equal to 0. Don't try it for negative numbers. So we have two new rules for negative numbers. Integral of x minus a to the power minus 1 dx is x minus a to the 0. What it tells us is integral of concentrated load is uniform load. Similarly, integral of x minus a to the power minus 2 dx is, remember this is all ramp, this truncated function business, is concentrated load, that is x minus a to the power minus 1. This is not at all like polynomials. So these two are special, not like polynomials. I want you to understand that. These are just rules that enable us to do all kinds of complicated things. Okay. Now with this rule, let's try something more interesting, which is the following problem. Beam, and I have my roller is here. So it's a beam with an overhang. That's it, that's the load. So what do we do? Okay, first thing to notice is that we are going to look at anything, we are going to abandon the two ends. So this end is gone, this end is gone. In the middle there is this roller, right? So we are going to represent the roller by a concentrated load which is pushing up. Let us call this A, B, C. So at point B there is a load which is called dy. That's the only load on this beam. The two ends, we are going to ignore them. We are going to utilize them at the time when we apply boundary conditions. Okay, so what is Q of x? It's obvious to you that this is a concentrated load. If it is a concentrated load, Q of x will be, remember B of y, this is positive up. So it is B of y times, let us say this is at location x equal to 0.5. The total length is beam is 1 meter. So it's 0.5. So it's x minus 0.5 to the power minus 1. That's concentrated load. That's all. Now we are back in business. What do I mean? So now we will be integrate this, and if you integrate the concentrated load, you will get x minus a to the power 0, right? So you will get dy times x minus 0.5 to the power 0 plus v naught. Remember, don't forget the constant of integration. M is dy integral of this. Now we are back to this kind of a setup. We are back to this. So M will give me x minus 0.5 to the power 1 plus v naught x plus m naught. Theta would give me dy times x minus 0.5 over 2 plus v naught x squared over 2 plus m naught x plus theta naught. And then what's the last? Y equals 6 plus m naught x squared over 2 plus theta naught x plus y naught. So as usual, we have 4 boundary conditions. I'm going to highlight them. 1, 2, 3, 4. But we have one more here. You see that? I'm going to highlight it in a different color because I want you to see that there is one more. We'll have to find these 5 values. Let's see whether we can. Okay. So now let's apply the boundary conditions at x equal to 0. What do we have? Well, we have fixed, which means that y0 equal to 0, theta 0 equal to 0. As usual, remember these are angle functions, and if x is less than 0.5, we don't care, so immediately you will get theta naught equal to 0, y naught equal to 0. Then at x equal to L, which is equal to 1, other end, it is free. See that? It's a free end, this end is free. So if I have free end, immediately I will get E at L equal to 0, M at L equal to 0. So what happens? Now if I compute that at L, so this means Vy times, let me draw the angle bracket, 1 minus 0.5 to the power 0 plus V naught equal to 0. And this is, since x is greater than 0.5, this thing will become 1 because it's 0.5 to the power 0, which is 1. ML gives me Vy times 1 minus 0.5 to the power 1 plus V naught times 1 plus M naught. This immediately gives me V naught plus Vy equal to 0. 1 minus 0.5 to the power 1, angle bracket. Remember, x is greater than 0.5, so this we might as well drop the angle bracket and replace it with the regular bracket. So By, so that is 0.5 By. So this thing becomes that plus V naught plus M naught equal to 0. So immediately we got V naught is minus By, M naught equals, I don't know whether it's obvious to you, if you subtract this thing out, you will get M naught equal to minus 0.5 By. But we still don't know By. What are we going to do? Well, if you look at x equal to 0.5, we have to have y equal to 0. So, at x equal to half, y must be equal to 0. That is how we find that's the additional equation. So, y is this? If you put x equal to half, I should get, the first term is gone, x, so put x equal to half, and you'll get x equal to 0.5, and you'll get y equals dy over 6 times 0.5 minus 0.5 over power 3 plus v naught times x cubed over 6, that is 0.5 cubed over 6 plus m naught times 0.5 squared over 2, and then the other two constants are 0. 0.5 times 0.5 over 3 is 0, so you will get 0.125 V naught over 6 plus 0.25 M naught over 2 equal to 0. From that, theta naught is 0. So those two things are gone. That's fine. I'm going to find something very, very silly. I'm going to find Vy equal to 0. It should be obvious to you that that's the case because this is a completely unloaded beam. Can you see that? There's no load on the beam. So I made an interesting mistake, but my calculations worked out fine. But I didn't load the beam with anything. That's why I got everything was 0. So it was just a propped up beam. Of course, I should get everything 0. Okay? Let's try another problem so that we are sure how to do this, which is this. So I have a beam with a nice little overhang. Built-in beam. And I have a propped up setup here, and I have 1000 pounds here, 1000 newtons here. This is 1, this is 1, that's 1. So, step number 1, I want you to do. So, pause here and write down Q of X for this. Okay, so please pause, write down Q of X, then come back and take a look at what I got. That's the best way for you to learn. Okay, so did you pause and check? Good. So this one looks like this. I ignore this end, I ignore that end, and my external load looks like this. I have 1000 newtons here, and I have, this is not a free body diagram, by the way. So please don't think this is a free body diagram. This is not. This is just a load function. What is the external load on the body? That's all I am listing. This is not a free body diagram. So this is again, let us call this A, B, C, and then By is there. And now I have 1000 newtons. So you should be able to write down that Q of X is upward positive. That's the most important thing to remember. Will be minus 1000 times x minus 1 to the power minus 1 plus dy x minus 1 to the 0, sorry, minus 1, x minus 2 minus 1. Rest of the stuff should be relatively straightforward for you. So I'm just going to write down v of x m of x. Before you watch me do it, I want you to do it so that you are sure about how to work it. You get this? Good. My last thing will be y of x. It will be minus 1000 over 2, that's 500. So I'm going to write it as 500 over 3 ei times x minus 1 cube plus by over 6 ei times x minus usual constants, the usual suspects are here. The only thing that's the additional one is going to be here. My additional one is going to be there. Okay? So as soon as I do this, now I got to apply boundary conditions. I'm not going to solve it, I'm just going to list it. It's your job to solve it, okay? So I got y0 equal to 0. Figure out how I got that. Theta 0 equal to 0. So this immediately gives me y0 equal to 0. This gives me theta 0 equal to 0. So I don't really have to look at this. I don't really have to look at that. And then I have free boundary conditions. This is at x equal to 0. Then y at L and y at 3. So free condition at x equal to 3. So v3 equal to 0, m3 equal to 0. So if I do that, I will get, this means that if I put 3 there, I'll get minus 1000 plus Vy plus V0 equal to 0, minus 2000 plus Vy plus V3V0 plus M0 equal to 0. Those are the two conditions I will get. Then the intermediate condition at x equal to 2, I get y equal to 0. That's the other condition which will give me so x minus 1 to the cube. Right? X minus 1 to the cube is minus 1000 over 2 EI. Sorry, minus 5000 over 3 EI. And x equal to 2, Vy, that term is gone, plus V0 times 8 over 6 plus M0 times 4 over 2 equal to 0. So if I put EI equal to 1000, then I'll get, this gives me minus 5/3 plus 2 and 4 V0 over 3 plus 2 M0 equal to 0. We got these two, A, B, C, solve A, B and C, and found all the functions. Plot on Excel and voila. I want you to understand that once we get this, once we get q of x, everything else is just brute force, just integration. There's nothing to it. So I want you to understand that drawing shear force, I mean getting shear force functions, bending moment functions, there is nothing to it. That's why we are all kind of surprised why you guys are struggling so much with this. It's actually much simpler than you think. You just have to remember that you have to get an expression for the external loads barring the two ends. Don't worry about the beginning of the beam and the very tip of the beam. But everything else, if you get the external loads and then you add constants of integration, you will be home free. There is nothing more to it. That's all there is. That's all there is. Okay? I hope you learned some of this and you'll get a chance to try this out on Tuesday.